Today, the internet won't stop talking about AI agents. Claude Code replaces more and more developers with every new Opus release. And OpenClaw is taking jobs by doing any computer task instead of people. Demand for RAM and Mac minis is going through the roof. But most people don't even understand what AI agents actually are and how they are different from regular ChatGPT. So in this video, let's break down all the types of agents. We'll dig into how they work, their limitations, different architectures, and what you can actually use them for right now. Hey, my name is Oleg. In my day job, I'm a software engineer, but on this channel, a web coder. Here I test AI models and tools, build micro projects and automations. I look at what actually works and what doesn't. Every day, millions of people use ChatGPT. It became a part of our lives a while ago, changed some habits and work approaches. Even though talking to an AI assistant is just predicting words based on the previous text. During training and through system prompts, neural networks were tuned to respond in a conversational format, creating the illusion that someone is actually talking to us. What if we ask models to generate text in a different format? For example, converting data from one structure to another, or classifying incoming text. This approach works well and is widely used in automations. You can build something interesting out of just a few LLM nodes. For example, in n8n I built a pipeline like this. Here's how it works. A message comes in from Telegram. The model figures out what type of content we want to generate: image, video or text. Then, depending on the choice, it processes the original message through an LLM in different ways, getting a prompt for content creation. After that, it generates an image, a video or just sends a text. Here's an example of how it works. I ask it to generate an image and get the result. Here, the LLM can influence the result and improve our ideas. However, the model can't make decisions or take actions outside the given boundaries. It can't generate two images instead of one or change text-to-image model until we manually adjust the pipeline. This kind of process is usually called deterministic workflow with AI elements. The neural network here only does two things. It makes local decisions by picking one out of a limited set of options, and it converts data from one format to another. The LLM can't fundamentally change the message processing flow. Some tools are there, but the system isn't really agentic. So then, what is an AI agent? Let's look it up. An agent is a system that can set goals, plan actions and use tools like browser, API, CRM to solve multi-step tasks without constant human supervision. Unlike regular chatbots, they don't just answer, they take action. Our current bot has no choice but to respond to us, and it can't really plan anything. Let's give it some free will. Here is a workflow in n8n that works differently. I used the AI agents node and connected tools for content generation and sending materials to Telegram. As you can see, there is no strict sequence of nodes here. There is just one LLM module that makes decisions, and tools are placed on the same level relative to each other. Now the agent isn't required to respond to us at all, but at the same time it can respond more than once. It can perform several actions in response to a single message. For example, I can now ask it to generate both an image and a video at once, or 3 images at a time. This works much more flexibly. The agent can actually decide and act independently. But our bot doesn't remember anything. It has no idea what was said before. Its memory is limited to a single processing cycle for each user message. Let's add a basic simple memory module to our bot and ask if the agent remembers previous messages. Great, now its memory looks back 5 messages, since we set the memory key plus a memory size of 5. This kind of chat history storage is simple to implement. It works fine in short chat sessions where the agent does a small task that fits within the model's context. Context is like the working memory of an LLM. Context size determines how much information the model can handle in a single call. Let's look at what tools our agent actually uses. To generate images and video, I gave it Fal AI tools. In them, I specified predefined models and some parameters. I did this to simplify the calls and minimize errors. as each model has its own required fields, sometimes in unique formats. The problem is, when it gets an error from a tool, the n8n crashes and stops the task. The fix for this is pretty hacky. So let's move to a different system that I think is more powerful and flexible than n8n. Let's take Codex CLI. It's a terminal-based coding agent from OpenAI. It can edit and read files, run terminal commands, and it can work on a ChatGPT subscription with generous limits. You can choose only OpenAI models in it, but they've been really good lately, so that's not a problem. I'll open VS Code, create a project folder and open it. And just for the demo, I'll ask it to make a simple browser app for cropping and resizing images. As you can see, while running, our agent starts calling different tools. It thinks and sometimes leaves comments. In the work log, you can see how it changed files and added code to them. You can also see that it tried to call playwright but crashed with an error. And as you can see, it didn't stop working on the task. In this regard, Codex is much more reliable than n8n. Then, at some point, it asked for manual approval of a command it wanted to run. This is a cool feature that comes with all coding agents. Within a project or globally, we can save a list of tools whose execution we consider safe enough for the agent to do without our approval. For example, reading files in the current project. But other dangerous commands can only be run if we confirm them on our end. In proper agentic systems, this kind of manual approval will almost always be present in critical places, but absent where there is no risk and where agents do great without human input. Alright, let's see what our coding agent built. Let's open the file. The app works. The selection area display is definitely non-standard, but the app is functional. Images get cropped and resized. There is even an output format selector and quality level. Nice. Let's do something cooler, since we have such a powerful model and a robust system. Let's create a Chrome extension. It will analyze content from YouTube recommendations and mark low-quality videos with a special overlay, so you don't waste time watching them. This is the prompt I came up with. I asked it to build not just the extension itself, but also its backend and a landing page with instructions and the download button. Plus, deploy the backend and landing page to my Qlify server. Before starting, I'll write the necessary stuff in env, adding my API key, base URL and model. I'll also initialize my rules for the project, and now let's start development and wait. After 40 minutes, the agent finished. It built and deployed everything. The landing page and backend are indeed working. But how did it even do that? To deploy the app to my server, it used Qlify MCP. MCP is a protocol for connecting various custom tools to AI agents. Qlify is my management panel for deploying different apps on my server. I vibe coded my own MCP and installed it in Codex with my API key. And that's it. Now my agent can deploy apps whenever I need. And by the way, the same goes for GitHub MCP. There I limited the scope so the agent can create private repositories and pull requests. However, let's look at how our extension actually works. It installs successfully, but on YouTube it doesn't really affect the content. The browser logs are full of errors. There are clearly issues with YouTube's blocks. Let's ask the agent to fix it and use some workaround or API. After a couple of such fixes, we got a working version. Some videos are actually getting marked with overlays. Cool. It considers all music videos to be junk. Okay. And let's test the feedback system. I'll write that I love Korean history. Okay. Yeah, my filtering prompt, based on preferences, has actually been updated. Cool. Everything works. A decent starting point overall. Good enough to test the feature yourself and then refine the product if needed. Now let's look at the console. When you watch the agent working on complex tasks, you'll notice a percentage showing how much free space is left in the context. That is 100% minus the current chat size divided by the maximum input size the model can accept, shown as a percentage. It drops towards 0. Then it hits near 0 and jumps back up to around 70%. How does it work? It's simple. Our chat gets compressed, via LLM summarization. At some point, when the chat gets close to the limit, a special Codex summarization prompt is invoked along with the entire chat history up to that point. The output is a smaller chat, and it keeps only what the model considers most important. This trick lets you keep working in the same session instead of getting stuck when the chat grows too large. However, this can also accidentally lose truly important information. Plus, in super long multi-hour sessions on huge tasks, it simply won't hold up. During the history compression, it's often impossible to know in advance what information will actually be needed later, since we might not know the full scope of the task or all future problems. So on long sessions, summarization happens many times, and at some point nothing remains from the original input task. It kinda dissolves into a homeopathic prompt. The current project was built by the agent with 4-5 compactions. In my case, nothing terrible happened because of it. However, after a few more prompts, it no longer remembered that it should be deploying new fixed versions of the backend to my CLI server. I had to push it along manually. Another solution to the limited context problem is trimming. It is a limitation of the number of messages that model receives to the fixed count. It only considers the last X number of messages. The context won't run out, but information about older discussions is completely lost. It's a pretty rough approach. It's used, for example, in the previously mentioned n8n simple memory node. And another approach is rewind or undo. With this we can go back to some earlier checkpoint in the conversation and continue from that old point. This doesn't solve the finite context problem, but it can help you roll back to before errors or hallucinations. You can also combine approaches. For example, in my micro project FunFi Studio for generating really long stories, it uses both summarization of old chapters with fact extraction and trimming, which only passes full text of the most recent chapters. And the user can roll back and regenerate chapters if something went wrong. Anyway, in its pure form, chat history as memory approach works well only in short chat sessions, if the user wants to build small task or project. For bigger tasks, there is a more elegant way to deal with memory problems. It's called sub-agents. For a demo, let's switch to Claude Code. It's an alternative terminal agent from Anthropic. It can also work on a subscription, though with slightly more modest limits. Working with sub-agents is much more convenient in it. Let's launch it in an empty project and create our sub-agents. Sub-agents in Claude Code are subordinate coding agents. They have their own separate context, tool access, and system prompt, basically a role. They also usually have a prompt that describes exactly when to call them for task delegation. As an example, let's create front-end and back-end developers. We go to /agents, hit create. Claude asks us to enter the agent's role. I will not overthink it this time. Ideally, in these roles you can specify exactly which approaches to use, which tools and commands to call. The role prompt lets you customize the system prompt for sub-agent tasks. Here are the prompts that Claude auto-generated for us. Let's also create a deploy agent to roll out our project to the server. I'll write this prompt by myself, so it clearly uses my CLI tool. For a test, let's create a micro web application for generating looped videos. It will generate images based on a prompt, then videos based on those images with the right start and end frames set, so that the final video loops seamlessly. Here is the prompt I came up with. For generating accurate prompts, I'll use Gemini 3 Flash model. For images, Fal AI. Here is the env file with the configs I prepared. I launch it, and after some time I see the sub-agents, backend and front-end developers. Then the deployer kicks in, rolling the project out to my CLI server. Great, after a couple more fixes, the project sort of works. The videos aren't looping like I wanted, but it's okay for now. Now we can look into the logs. We see how the main agent delegated tasks to its subordinate workers. For example, it wrote in a task, built a backend for this system, and the backend agent picked up the task. So the code details and implementation lived only in the backend developer's context. Front-end details similarly stayed in the front-end developer's context. And the main agent's context only held the big picture, my requirements and the coordination of all agents. This approach splits all the necessary tool calls across 3 contexts, which can sometimes even run in parallel. We get not just more total memory, but also time savings. But what if your project is so big that it needs 10 backend devs and 10 front-end devs? Then creating 10 sub-agents manually will be pretty hard. Plus, you'd probably need peer-to-peer communication between workers, because it gets harder for one lead to coordinate that many. To solve this problem, Claude Code introduced agent teams. Let's see how it works. In another folder, let's ask it to build the same project, but make it super convenient and polished. Plus, properly verify from the start that the backend and frontend work correctly by writing tests. Right now, agent teams is an experimental feature, so we force enable it through this config variable. We run it in the terminal. I see the teamlet created two subordinate workers, backend and frontend devs. I didn't describe them anywhere. The main agent decided on its own who it needs and how to distribute tasks. We can also look at the work history of each subordinate agent here, see what they are doing. Agent teams are especially useful when you need to do giant tasks on huge code bases. For example, documenting an entire code base by creating 10 analysts agents for 10 project models. This works fine. After some time, our project is ready and deployed. It works right away. The result came out slightly better than with sub-agents, but the video still won't looping and had audio, even though I explicitly wrote the exact parameters in the prompt for cooling the video model. How can we fix this knowledge loss? We can use Claude Code's built-in auto-memory. Thus, the agent will save important facts into a memory store for this project and retrieve them if needed. To activate auto-memory, we turn it on with this flag. Now, after restarting Claude Code, this feature works. I'll ask Claude to remember that videos should be generated without audio in this project. We can see it read and saved this to memory. If we look in the Claude projects folder and go into my project's memory, in the memory.md file we'll see exactly the info we need. To verify, let's ask it in a separate Claude Code session if it remembers anything. Yes, it remembers and everything works. In different agentic systems there are many similar tools. They let agents decide what and when to remember and then how to retrieve it. In Claude, auto-memory reading works like this. The first 200 lines of the memory.md file are simply injected into the agent's system prompt. This file can contain links to deeper hierarchies of other MD files. If the agent spots something useful for a specific task, it can dig deeper. A similar approach is the memory bank pattern, where we store project info in a specific folder. And there is also a very popular approach, reg. In it, we store information in a vector database and search it by keywords, using meaning vectors embeddings. This technique is used in practically all agent systems. It is effective when you need to search through a huge information base, when other approaches simply can't hold that much. To test this approach in Claude Code, you can connect a reg MCP that opens the necessary tools. Let's check. I'll ask Claude to add my bank statements from the last few years into our reg store. When it's ready, I'll ask in a separate chat what I spent money on in Tbilisi. You can see how Claude calls the reg tool with a search for spending in Tbilisi, and it returns the correct result. If we look into the tool results folder in Claude, we can see the raw response from our reg tool. It returned the top 20 results matching the query. Each result is one page of a bank statement. You can see that the top result is exactly what we needed. Page 6, which has the spending in Lari in Tbilisi. And another cool thing about terminal agents like Claude Code and Codex. They can be called from inside another program with a task to execute. Since they are purely command tools, this is super easy to do. Also, these calls can work on a subscription without paying separate API costs. As an example, let's wrap our agent into Telegram bot. I want to talk about my expenses in a comfortable interface. I launch it, and after a few minutes I get a working program. Now this Telegram bot can search through my bank statements in the same way. And what's also cool is that it can do everything regular Claude in the terminal can. For example, I asked it to develop and deploy a snake game to my server. It did it and it works, though it doesn't have memory between restarts. So after a restart, I had to remind it what it was doing before. But then an idea comes up. What if we ask the bot to improve itself? Let's try. Let's add memory between restarts and memory collection via the /start command. Plus image recognition, since right now it can only read text. Awesome. But now the bot reminds me of something. It's almost identical to the viral OpenClaw. The difference is just in the details and the number of pre-built integrations. As you can see, building your own universal self-improving personal agent is super easy right now. Since our bot is a personal assistant, let's give it some long-term memory. Let it remember facts, preferences and some things about me, so I don't have to explain them from scratch every time. There are many solutions for implementing long-term memory. We already talked about context manipulations, auto memory in Claude, and reg systems. Let's look at a slightly more advanced approach to long-term memory. We'll use graphs to store facts and connections. The most convenient open source option for our case is mem0. Since LLM is called internally to process facts, we need to set up some variables. Gemini 3 Flash API and OpenAI credentials for embeddings. Done. After implementing it, let's check how it remembers my name. We restart the session, and you can see it remembers my name. I also asked it to build a memory graph preview so we can see how connections are stored. Here's what it looks like. You can see that besides my name, it also saves some facts about project files and libraries being used. How does this work? For every message sent to the bot, the user's text first goes through a search for relevant memories using reg and the graph structure. For graph search, facts are extracted from the text and similar nodes are found via reg. Then the nearest neighboring nodes are collected. The found facts are added to the model's context, and then the model responds to the message with this information in mind. After that, the user's statements are added to mem0. Then the LLM breaks them into facts and updates the connections graph plus our reg. As an alternative to mem0, you can also look at ZEP. Their system also accounts for fact timestamps, ranking them by relevance. Looks interesting, but unfortunately the community version is no longer supported. New versions are only released as cloud solutions. So now our agent has pretty solid long-term memory. But the agent sessions themselves are short-lived. We can't expand the context window of neural networks. So we limit it by the size of tasks we can give to our agent. But honestly, I want to have a giga agent that can take on tasks of any size and duration. For example, getting 1000 subscribers, making $1,000 or something truly complex and continuous. In theory, this is possible if we split the agent into a huge number of sub-agents. Each one will handle a small task and have access only to the piece of information it needs, so we don't overload the context. To make this happen, I came up with this algorithm. The user gives a task as input, the agent evaluates it. It can either take it into work directly in the next iteration in a separate session or break it down into subtasks. The subtasks follow the same recursive algorithm. After all subtasks over tasks are completed, an aggregation session runs. It assembles the results into one combined output. Then comes the evaluation stage. Is the task done? If not, the main task can add another batch of subtasks for the next attempt to solve it. This way, it can keep trying to solve some part for a long time. Plus, all tasks can enter a wait status at the evaluation stage to request human input or simply wait for some time. This is useful for long-running things like making changes to a project and waiting for metrics. Let's build it. After a couple dozen commits and a couple of days, I got a working mechanism. Here, for example, I asked it to give me a PDF comparing digital nomad visas in all Asian countries. The agent broke the task into researching regions, then those regions are split into specific countries. In another branch you can also see research into taxes, nature, climate and other factors. In the end, this system carefully studied all the data, aggregated it, verified it and assembled as PDF like this. Looks pretty good. For comparison, GPT Pro at $200 assembled a similar file. So the system is at least roughly on par with GPT Pro, but it needs testing on even harder and more complex tasks where GPT Pro can no longer keep up. In the future, I'll try adding some kind of evolutionary self-improvement mechanism to this agent, plus the ability to add new tools like it's done in OpenClaw. In conclusion, I would say that agents are really picking up steam lately. The newest LLMs are taking on bigger and bigger tasks. You can assemble increasingly autonomous workers from them. And now we need to learn how to manage them properly. Build workflows, implement AI into the right places. Learn to delegate work tasks to them, fine-tune and build pipelines. All of this is pretty amazing. I'm excited to see how the world will change this year. Subscribe to the channel, I'll keep you posted. That's all for now, see you around.